Welcome to the Chem 100. I guess it's called review session, but certainly time when if you have questions or you need me to clarify certain things, then you have the opportunity to ask questions. That way, if you're learning on your own, reading the notes, reading the book, and you need clarifications, then you can talk to me in this session, and perhaps everyone will benefit. I also put some topics on my iPad, indicating the important topics that are covered in Chapter 1 and Chapter 2. Chapter 2 is really all about math, and these are the essential topics that you guys will need in order to navigate the rest of the course. Probably the most important is dimensional analysis, because as scientists, you guys will be solving problems, math problems, and dimensional analysis is actually a very good technique to solve a lot of math problems without having the equation. So what I want to do, you'll see me looking in that direction a lot of times because I have another laptop, because I want to see what you guys are seeing, because as a host, if you ever are a host in Zoom, you can only see the screen in front of you and you think that you're sharing a document, but you're not really sure. So by having your view, I can see exactly whether or not it's the right item, as well as the fact that I can see on that other screen who the participants are, as well as if you have any questions, if you write something in the chat room. Okay, if you do have questions, then please feel free to unmute yourself and fire away, or if you want, you can also type it in to your in the chat room there. But before I start, let me just remind everyone that this is being recorded. What I will do is I'll take the session, kind of edit it out, and then repost it in Canvas. I'll probably put something in the announcement that this is the Zoom session that was taking place on February 11th. What I want to do, though, is I want to answer any pressing questions that you guys have. If there's no pressing questions, I'll just highlight some of these topics, and then maybe you have questions as I discuss these topics. But it's really a session for you, okay? I know it's difficult to study or try and comprehend things on your own. And usually what happens is that if you're new to the sciences, or especially chemistry, you have a lot of questions when you're reading these materials. Sometimes you think that the questions are maybe too dumb to ask. They're not, okay? You need to ask them so that you get clarification. Because if it's not clear in your head and you can't explain it to someone else, then if I ask you a question to probe your knowledge, then it's going to come out blurry. Okay, so please make sure that as we go through the discussion, if there's things that you need to bring up, that you do bring up. This session is really for you. Thank you for filling out the doodle survey, and this seems to have the most vote. For those of you in lab, tonight at 8 seems to be the one that has the most votes. So after today's session, which should go to about 6, unless you guys have a lot of questions, then we'll take an hour break and continue on in the lab, in the Canvas lab session. And in that particular session, I'll give you guys a preview of what experiment 1 is about. But it doesn't look like you guys have anything in the chat. Let me go ahead and at least talk about the topics that are here. Chapter 1, there's a bunch of information there, like your study habits as well as problem solving. You want to do the problem solving survey so that you can get some bonus points. Let me show you Canvas real quick, because remember that there's a bunch of assignments that are due this weekend. If you don't take advantage of them, then you lose the extra credit opportunity. So let me do that and show you what's up. Okay, so this is, let's see, this is my internet. Let me blow this up so that you guys can see this. And if you go to, always navigate through the module, because that's the way the course is organized. Here's just some background information about the course, okay? But right here under module 1, which takes us from February 1st to February 7th, that's the first week, which was last week. You'll see at the very bottom here, a collection of extra credit. And you want to do these if you want the 5 points bonus. If you don't want them, fine. But you notice these things are due Sunday. So if you want the bonus points, then please participate and do these. This last item here, which is due February 16th, is the syllabus quiz. So if you read the syllabus quiz and you take that, you have 1 hour. So make sure you're prepared. It is open notes, so you can have the syllabus in front of you, but you are limited to 1 hour. I think it's 50 points. It's a bunch of true and false and fill in the blank. So that's some bonus points. And if you want points in this class, you want to take advantage of that. So I'm going to collapse this so that it's easy to navigate. And then here is where we are. Chapter 1, Chapter 2, and Chapter 3. Your next quiz is going to be on next week, February 21st. If you open this, it'll tell you, okay, the game plan in terms of how this thing operates. And this is a 90 minutes and it's 50 points. And there's about 25 questions, multiple choice, etc. And it tells you right here, it opens February 19th. That's on a Friday, a little bit after midnight, Thursday, Friday. And then it closes on the 21st. Okay, so you've got 3 days, Friday, Saturday, Sunday, to find time to do the quiz. Once you open up the quiz, then the clock runs, unless and you have 90 minutes. If you're a DSPS student, then you're allocated more time. But once you open it and you answer the first question, it'll start counting down from 90. If you take a break, let's say you take about 30-minute breaks, then the clock still runs. You're going to have 30 minutes less to complete the quiz. And also try not to take it like at 11:30 Sunday evening, because it'll shut down by 11:59 Sunday, no matter what, even if you don't have the full allocated 90 minutes. It is open book, open notes, no open friends. So if you have your book, you can use that. So please keep that in mind. That's next week, okay? So again, if you go to module for module 2, which is what we are in, it covers chapter 1, 2, and 3. After each chapter, there's a homework link. You can click on that. It'll take you to My Lab and Mastering, which is this link right here. And it should open it to this link right here. And it should open it up to that chapter. So try to make it pretty simplistic in terms of where to navigate and how to get there. So if there is some confusion, some of you already emailed me and point that out. And so that's kind of good, because then I can help the rest of the class. Okay, so that's where you want to concentrate for until the 21st. And then of course, we just go down the sequence here. Module 1 goes from February 1st to the 21st, module 2, 22nd to the 21st of March. And all you need to do for that particular section is just stay within that module. Okay. So let me go ahead and start this. Well, I don't see any questions in the chat, so let me talk to you about the scientific method. Okay, and scientific method is really covered in chapter 1, and you guys will need to know the components of the scientific method. And the reason why you need to do that is because your first experiment as well in lab is about the scientific method. And the scientific method is a way of organizing the knowledge that we've gained over the years. The knowledge that we've gained over the years, that mankind has gained over the years, kind of helps us understand the universe better. Okay, and so what are the components of the scientific method? There's usually a question or an observation. And so it's something that sparks an interest. And what scientists do, or what any person that wants to gain knowledge do, is they try and answer the questions or explain the observation. And so that's called a hypothesis. There is no evidence that that hypothesis is true, but it's simply to try and explain the observation or answer the question. Like, for example, you see a fireball coming up from the east every morning. And for the longest time, people thought that was a god rising from the east and then setting in the west. And they rode their chariot across the sky. And so that's a hypothesis. It doesn't have any basis, but it's an explanation. It tries to explain what's observed. Of course, after the hypothesis, you got to try and prove that. And so you try and do experiments in order to validate the hypothesis. Okay, so experiments might be taking some measurements or making sure that under controlled conditions that these things do happen. And then if the experiments validate the hypothesis, then you can say, yeah, there's some validity to the hypothesis, but it's still a hypothesis until there's many experiments that sort of prove that it's true. So the experiment sort of, you make some predictions with that experiment, okay? And then you validate it, or if it's not validated, if it's not true, then what you do is you change the hypothesis. Okay, if the evidence states that that explanation is false, then you've got to change it. Otherwise, you're fudging the data, or that's what people will do. So you can't really do that. But if you have enough experiments to validate that explanation, then that hypothesis becomes a theory. And it's basically just a cycle in which you do experiments and you validate it, and then you kind of keep supporting or validating that explanation. Eventually, the theory is going to carry a lot of weight, and maybe from this whole thing, you get something called a natural law. A natural law simply states what happens. Okay, like, for example, the law of conservation of mass. It tells you what happens in terms of mass. It doesn't try and explain anything. The law of conservation of mass tells you that mass can neither be created or destroyed. It's simply converted from one form to the other. Notice there is no because in that statement. It just tells you the way it is. There's also something called the law of conservation of energy. Energy cannot be created or destroyed. It's only converted from one form or the other. There is no explanation. It just states what we've always known. So that's basically the framework of the scientific method. When you guys do experiment number 1 next week, you guys are going to have a question. What happens to the mass of a penny with age? And your hypothesis will be, Well, maybe it gets heavier. Why does it get heavier? Because there's always a because in the hypothesis. Because over time, it'll pick up dirt and grime. It'll get oxidized by the air, and more atoms there will make the older pennies way heavier. On the other hand, some of you might say, oh, it's going to get lighter because there's going to be wear and tear. When you have wear and tear, the copper atoms at the surface of the penny are going to be rubbed off. And so older pennies are going to be lighter. But these are our hypotheses because they try and explain the question, what happens to the mass of a penny with age? And then you do the experiment. The experiment that you guys will do is taking a bunch of measurement. You will weigh a series of pennies. That's why you need to collect some pennies between 1960, if you got old pennies, even if you got 1934, that'd be great. Older pennies before 1980 and newer pennies after 1985. And you guys are going to weigh that out, and then you're going to see whether there's a trend. Are the older pennies heavier than the newer pennies or vice versa? And you're going to validate that hypothesis, or maybe you're going to come up with a new hypothesis. But that is, we do the experiment, the penny experiment, to kind of demonstrate how the scientific method is carried out. And you guys do the scientific method all the time without even knowing it. You wake up in the morning, you have to go to work, and your car don't start. Okay, so the question is, well, why won't my car start? So the you think, oh, it's probably because my battery is dead because I left my light on. So that's a hypothesis. So you do the experiment. You go in and you might have a voltmeter, and you determine what the voltage is of your battery. So these are things that you don't do in an everyday basis without even thinking about it. Okay, so that's what I mean by the scientific method. So cross that out. Let's take a look at scientific notation and significant figures. And what I want you guys to look at in this particular case is make sure you read the notes, because the notes gives you some concrete examples of these things. And let me just see what's going on here. Okay. Okay, so in chapter 2, if you look in Canvas, or you go to my website, you'll see lecture notes pertaining to these topics. So this happens to be uncertainty and significant figures. But before I do that, I do want to talk to you guys about scientific notation and exponential notation. You guys are going to have to learn how to write very, very large numbers or very, very small numbers via the exponential notation format, because it's a way of saying, expressing the same numbers in a way that shortens it. Okay, there's a question here. When you have a chance, if you could briefly please talk about significant. Yeah, that's what I'm doing right now. Okay. So let's take a look at exponential notation and scientific notation. So suppose I have a number like 1, 0, 1, 0, 0, 0, 0, 0, 0, 0. You can see that this is a large number. If you were going to read this in terms of just reading it, you know, this is the thousandth place, this is the millionth place, this is the billionth place. So this is 1 billion. 1 billion, right here is 1 billion, 10 million. This is basically a 1,010 million. That's that number. Okay, this is the million place. This is the billion place. If you try to put this in your calculator, you're going to run out of room. So the question is, well, what's a convenient way of writing this number so that you don't lose any of the digits, but yet you can compact it? So you can write this number as 1010 times 10 to the 6. Okay, 1010 times 10 to the 6. And that would be a way of writing this number in terms of exponential notation. And that's because we are writing these zeros out here as that exponent. And so we're basically describing the size of that number. Okay, you could also write this number as 1.01 times 10 to the 9th. Yeah. Okay, and so writing it as 1.01 times 10 to the 9th is this number, and it's also the same as that, but the difference between both of these is that both of these are exponential notation. Only this number is scientific notation. Now, what makes this number scientific notation? The fact that the digit is just to the right of that leftmost number. Okay, so when you put a number like 2300 and you write this as 23 times 10 to the 3rd or 2.3 times 10 to the 4th, both of these are exponent, but only this is scientific because you're putting the digit just to the right of the leftmost number. That's scientific. And that's what we want to do in order to do science. We want to write it in scientific notation. Okay, so remember that if a number is less than 1, okay, then what you do is you move the decimal point to just to the right of the first non-zero number, and you count how many places you're moving it. And because it's less than 1, now it has a negative exponent. That's 1.6 times 10 to the minus 3. On the other hand, if a number is greater than 1, then you're moving the decimal place to the left. And because it's greater than 1, then that exponent is positive. Now, when you type this into your computer, you can't do a superscript, which is what this is, okay, or a subscript. It's very difficult to type that in. So the way we do it in science is we write this number right here as 1.6 e to the 3rd. Okay, the e here, make sure you practice this, stands for times 10. Okay, and so when you write large number in my quizzes or my exam, don't write times 10 to whatever. Don't do this, times 10 caret 3. Too many characters. Just write E3 or E negative 3 if you're using that. The E stands for times 10. That's the computer format. So please keep that in mind. So that's what exponential notation and scientific notation is about. It's about taking large numbers or very, very small numbers and expressing it in such a way, in a compact fashion, that you get rid of these zeros that are really just placeholders. The zeros here just kind of tells you the magnitude of that number. It has no significance. It has no significance other than the size. Okay, like these 2 zeros over here, it just tells you that this 1/6 is to the 1,000th of a place, but the -3 gives you that same information. So that's what scientific notation and exponential notation is about. Now let's take a look at this topic right here, significant figures, because significant figures is one that is always a source of confusion for beginning science students, because it's so important and yet it's so confusing. Okay, and the reason why we have significant figures is because, like, if I wrote this number right here, then the only digits that really have meaning are the 1, the 0, and the 1. Those are the only numbers that have meaning. The others are just placeholders. It tells you the size. And so we need a way to express numbers so that all we see are the significant ones. That's why it's called significant figures. Okay, all we see are the significant ones. And so what I want to do is kind of show you this real quick and just go over this. Let me change the orientation here. Let's see. Yeah, here. This is in lecture note 2, and lecture note 2 basically reviews the significant figures. First of all, let me go ahead and do this. The story of this right here illustrates the importance of significant figures. This story is about a cab driver in Egypt. Before the COVID thing occurred, there are these cab drivers in Egypt that picks up tourists and tell them for a nominal fee they can drive them to these ancient ruins and tell them the history of these pyramids. Well, my friend goes in and decide to take up one of these persons on this personal tour, and they come up to a pyramid. Okay, they come up to a pyramid, and the cab driver says, yeah, that particular pyramid's exactly 4,518 years old. Okay, that's how old that particular pyramid is. And my friend does a quick calculation, and he basically, this happened in 2018, and he says, oh, so that means that this pyramid had its grand opening ceremony at 2500 BC, and says, yeah, exactly. And my friend asks, well, how do you know it's exactly 4,518 years old? And the guy says, well, when I worked here back in 2000, they told me it was 4,500 years old. Okay, they told me it was 4,500 years old, and I've been working for this company for 18 years. So I just add 18 years to that 4,500, and now I know it's 18 years old. So the moral of the story is that when they gave this person, that information, the 4,500 years old, the error in that number is plus or minus 100 years. Okay, the error in that number is plus or minus 100 years. And so if the error is plus or minus 100 years and this person's adding 18 years to that value, then they're totally incorrect significant figures. If you're given a number of 4,500 and the error on this, how do I know that the error is plus or minus 100? Because the only digits that are significant are the 4 and the 5. And so that 5 has an error of plus or minus 1. So it's plus or minus 100. And to add 18 to that, when the error is plus or minus 100, is doing a disservice. Okay, so that's the story as to what you are not supposed to do in science. You cannot be more precise than the error of the data that you have. Okay, you cannot say that something's 4518. Cannot say that something's 4518. All of a sudden, my thing is going haywire. When the error is plus or minus 100. Okay, 4518. You can't say that. So that's what I mean by significant figures. So let me go back and show you that in here. So when you guys take measurements, then the numbers that you record is going to be based on the digits that are significant. So it's very important to know what significant figures are. So a lot of times there is the question in terms of precision and accuracy. Precision tells you how close or how fine your measurements are. Accuracy tells you how close to the correct value you are. And so the difference between precision and accuracy, let's say that this is the true value of a measurement. So this are the measurements. These are both precise. Notice how close these measurements are and how close they are to the true value. These are both precise and accurate. This, however, is not accurate because it misses the mark right here, but it is precise because the measurements are close to each other. So this measurement is precise but not accurate. This right here is an accurate measurement because you notice that it averages right to the true value, but it's not very precise. Notice how it's scattered. And then this right here, well, this person who's doing this measurement needs to be fired because they are neither precise or accurate. Okay, so so that's the difference. Accuracy is measuring it to the true mark. Precision has to do with how close those measurements are. There's actually two definitions of precision. One is how close each measurements are to each other. The other is how fine the measurements are. Like if I measure, say, a football field and I measure it to the closest yard, okay, I've got the football field and I can measure it in terms of yard, but suppose I can measure it to the closest feet, that's more precise than measuring it in yards. If I can measure it in terms of inches, because it's more fine, that's more precise. So again, there's two definitions of precision. One is a collection of measurements and how close they are together. The second is how small, how fine those measurements are. The smaller the increment, the better precision you have. Okay, so that's basically it. And this just kind of shows you in this particular scenario, I'm going to skip this, what accuracy and precision happens to be. Now, let's take a look at this right here. Whenever you take a measurement, you're always going to read these, what we call tick marks or calibration mark. That's the why you have an instrument. Okay, they measure values, and it's up to you to figure out exactly how many digits you're going to need to take this measurement. So if you take a look at this right here, you'll see that, let's say this is a centimeter ruler. This is 0, 1, 2, 3, 4, 5. So you know that this measurement, this blue line, is between the 4 and the 5. So you can say it's 4 something. It's greater than 4, less than 5 centimeters. Now, if you take a look at the spacing between each tick mark, from here to here, that's 1 centimeter. So the rule of thumb is that if your increments are, say, 1 centimeter, then you're going to read your measurements to 10% of that 1 centimeter, or 0.1. So the delta, which is the difference between this line and this line, between this line and this line, is 1. And so you're going to be able to read your measurement to 1 more decimal place after that. So if you take a look at this right here, you can see that you can estimate this about 40% to the next line. So that means that this measurement's about 4.4 centimeters. You're not going to say 4 because that's not precise enough. You're not going to say 4.45 because that's too precise. That's like being the cab driver. You're going to say 4.4. Why is it only to the 10th of a place? 10th of a place is 1 digit over. It's because these spacing dictates how far you're going to read it. Okay, this spacing dictates how far you're going to read it. So let's take a look at another example. Okay, let's take a look at another example right here. You see how in this example you have finer calibrations. Let me just pull this up. Well, now you can see that this is 4, 0.1, 0.2, 0.3, 0.4, 0.5. So now you can see that that blue line is between 4.4 and 4.5. You're not going to say 4.4 because that's not precise enough. And you're not going to say 4.5 because that's way under. Okay, so what you're going to do is say, okay, it's 4.4. Those are the true values that I know, but then you're going to have to estimate that last digit. And because the delta on these, the spacing between the line is 0.1, then you're going to read it 1 more past that decimal, or 0.01. Okay, let me just remind you that the first digit after the decimal is called the 10th. The second digit after the decimal is called the 100th. The third is called the 1000th. So the fact that the delta is to the 10th, you're going to read it to the 100th. That's just the way we read these things. So this particular measurement If you eyeball it, it's going to be 4.4, like 3, or 4.42. It doesn't matter what that last digit is, but you're putting in that last digit to tell the audience that's the precision of my measuring device. When you guys do experiment number 2 in lab, you need to know that, because if you don't, then you're going to mess up your lab practical. You got to be able to know how to read measuring device. So let's move on. And I want to make sure that you see this also in this thermometer. If you look at this thermometer right here, you can see that this right here is 32, and that's 33. This is 32, 32.1, 32.2, 32.3. You can see that it's between 32.3 and 32.4. And the delta is 0.1 degrees. Okay, because if this is 32 and this is 32.1, so each increment is 0.1. So you're going to read this thermometer to the 100th of a place, 2 digits past the decimal. So I would estimate this measurement right here to be 1 to 32.35. Okay, you need 2 digits after the decimal point. On the other hand, this thermometer is less precise, because if this is 30 and that's 40, then this is 31, 32, 33. So this mark right here is between 32 and 33. So I would say 32.2 or 32.0. You need to say that you're going to read it to the 10th of a place, because the delta, the spacing between these are one degree. So one more past that is to the 10th. That's why this reading would be 32.1, 32.2, or 32.0. You need to put that 0.0 to tell the audience that the spacing between these lines are 1 degree. So hopefully that makes sense. Okay, you can read the contents here in order to do that. Here is the description on that. So let me move on, because the question here is, how many significant figures do these digits have? And if you know your rules of significant figures, then you might say this has 5 significant figures, or maybe you're going to say this only has 2 significant figures. If I ask you how many significant figures this number contains, you might say, oh, it's got 4, or maybe it's got 5, or maybe it's got 2. Okay, how about this number? You might say it's got 4, you might say it's got 1, 2, 3, 4, 5, 6, 7. And this, how many significant figures does this number have? Some students will say 2, some students will say 4. There's actually a very easy way to know the number of significant figures by just glancing at the number. And this is a trick I learned when I was a TA in Santa Barbara. Okay, and the trick is to come up with a weird analogy that is so absurd that you can't forget it. You will always remember it. So this is basically it. So this is a map of the United States. Over here on the left is the Pacific Ocean. Over here on the right is the Atlantic Ocean. So what you can do is place a number right in the center of that map. And if it's got a decimal point, this number has a decimal point, then you can say that the decimal point is present, Pacific present. So what you do is you draw a line from the Pacific Ocean to the first non-zero digit, And the first non-zero digit is 4. All digits after that, the 4, the 0, 0, the 5, and the 0 are significant. So this number has 5 significant figures. Okay, so it's a pretty easy rule. That way you don't have to memorize all the rules that they give you in terms of significant figures. This number has a decimal. The decimal is present. So you draw a line from the Pacific Ocean to the first non-zero. The first non-zero is 4. All digits, including the 4, are significant. This number has 4 significant figures. Let's see what happens. 5 significant figures. Sorry about that. Let's see what happens when you don't have a decimal. When you don't have a decimal, then you say that the decimal is absent. So it comes from the Atlantic. You draw a line from the Atlantic all the way to the first non-zero number, which happens to be, in this case, 5. As you go from right to left, all digits after the 5 are significant. So this number has 3 significant figures. Okay, so if you remember that, you will always know that this has a decimal. You draw a line from the left. It's got 1, 2, 3, 4, 5 significant figures. This number has a decimal. You draw a line from the left. The first non-zero is 1. There are 4 significant figures. This number has a decimal. You draw a line from the left, the Pacific, to 5, first non-zero number, 4 significant figures. This number does not have any decimal. You draw a line from the Atlantic, the 5 and the 2 are significant. So you see how that is easily figured out just by remembering this weird analogy. So that's basically it. This chart just tells you that this has 5, this has 4, this has 4, this has 2 significant figures. Don't worry about the implied uncertainty and the relative uncertainty or the percent relative uncertainty. Why? Because you guys don't need to worry about that. We're not going to be using that in that class. You just have to know about significant figures, because that's one of your first exercise in lab, is to know significant figures. So once you understand significant figures, then you can apply the rules of math to do these things. You see right here, this has 3 significant figures. This has 3 significant figures. This has 2 significant figures. This has 1 significant figures. If I were to ask you to add this all up in your calculator, then if you do so, you'll come up with 105.32. But if you wrote that in your answer key, I would mark you wrong. And the question is, why is it wrong? Even though that's what the calculator says. And the reason why it's wrong is because you see how this number right here gives you an error. The rightmost digit is your uncertainty. That's the number that you sort of guess. Remember when we were taking measurement? That was an estimate. So this digit right here has an uncertainty to the 10th. This number right here has an uncertainty to the 100th, 2 places over. This number has an uncertainty to the first place, not even the 10th, the first place. And this is to the 10th. And so which of these data has the biggest error? The biggest error is 83. So to report a number of 105.32 and tell me that my precision is all the way to the 100th, when my data has an error in it of plus or minus 1, is incorrect. When you do addition and subtraction, it's like this. Suppose someone gives you $2.52 in cash, and another gives you $3.26. And then the third person gives you 50 plus a bunch of pennies, but you're estimating these pennies and it's not really precise. So when you report these things, when you report the true value, the error is inherent in these pennies that you didn't count directly. The same thing when you add and subtract. When you add and subtract right here, and you write a number of 105.32, this has more precision than your data. Okay, that's why this number is incorrect. The way you would report your answer would just be 105, because this data right here has an error of plus or minus 1. So your answer must have the same magnitude in terms of the error. It has to be plus or minus 1. Okay. One more thing I want to mention is when you do addition and subtraction, you got to know the difference between precision, which is how many digits pass the decimal point, and significant figures, which is what we just talked about. So if you take a look at this right here, this has 3 significant figures. This has 2 significant figures. Okay, 3 significant figures right here, 2 significant figures right here. But which one is the more precise? Which one measures a finer measurement? The 1.2. That has a better precision. So the number with the fewest significant figures is 1.2. the number that is least precise is 123. Okay, let's take a look at this next one. And the reason why we're going through this is because when you do math operation, when you add and subtract, you got to look at precision. That's this column right here. But when you multiply and divide, you got to look at significant figures. So keep that in mind as we go through this exercise. So there's two numbers here. Which one has the fewest significant figures? Hopefully you guys said 1.23. Which one is the least precise? It's also 1.23 because that's to the 100th of a place, whereas this digit right here is 3 digits over. That's to the 1000th. And all these digits are significant because there's a decimal point right there. Okay, let's take a look at this next one. Which one has the fewest significant figures? It's going to be 0.0012. That only has 2 significant figures. Remember the Pacific rule? You draw a line from the Pacific all the way to the first non-zero number, the 1, all digits after that, the 1 and 2 are significant. This has 3 significant figures. Which one is least precise? Well, this thing goes all the way to the 5 places past the decimal. This only goes to 3. So the least precise is 0.123. Know the difference between significant figures and precision. Precision measures things past the decimal. Significant figures tells you which of the digits have meaning. Let's take a look at the last one. 30 and 3600. Fewest significant figures? Well, this only has 1. No decimal, so you draw a line from the Atlantic. The 3 significant. Here, no decimal. The 6 and the 3 are significant. So fewest significant figure is 30. Least precise, whereas this is plus or minus 10. This is plus or minus 100 because that 6 is 100 place. So the least precise is 3600. And so why do we need to learn that? Because of this right here. Going back to our previous question, figure out which of the data is the least precise, which is 83, because that has an error of plus or minus 1. You have to round off when you add numbers based on the least precise, because that has the biggest error. On the other hand, when you multiply and divide, this is another example. You guys can figure this out. We don't have time for that. Whenever you multiply and divide, this is a multiplication, you round off your answer based on the fewest significant figures. Fewest significant figures. So this has 3 significant figures. This has 2. Your answer, when you multiply and divide, has to be rounded off to 2 significant figures. This would be 7.5. That's the number that I would write down. There are different rules when you add and subtract, and you need to remember that. Okay?
Excuse me, I have a question.
Sure.
So at the previous one, it was 105, and you put the decimal at the end for the correct way to do it.
Yeah.
For the significant figures, is it 3 or
Yes.
is it 4?
It's 3.
Even though there's a decimal at the end?
The decimal just tells you the decimal is present. And then you draw a line from the Pacific. The 1, the 0, and the 5 are the digits that you are counting. You don't count the decimal.
Okay.
So it's 3 significant figures. Okay. Notice that you change, when you add and subtract, you change the number of significant figures. You went from like 1 significant figures, 2 significant figures, down to 3 significant figures right here. And you do that in addition and subtraction because you use different rules. You round off your answer based on the least precise. But this final answer does have 3 significant figures.
Okay, wait, so with that being said, we would only count everything on the left side. We wouldn't count everything on the right side of the decimal. We would only take 105, not the 0.32.
No, you don't want to do that. And the reason
Okay.
why you don't want to write down 0.32 in your final answer is because the 3 and the 2 is to the 10th and the 100th. Yet
Yeah.
this number 83 has an error of plus or minus 1. The plus or minus 1 has a bigger error than the 0.3 or the 0.02. You can't
Okay.
write more precision than the data that you have.
Okay.
Okay. So that's why you round it off to 105. This number right here, the rightmost digit tells you the precision, the uncertainty, which number has the biggest error. This 5 has the biggest error, plus or minus 1. So that's why you write it as 105 plus or minus 1, because your 83 is 83 plus or minus 1. Okay, you're not going to write 105.32 plus or minus 1, because 105.32 is plus or minus 0.01. That's not true for 83. Okay, so you always, in addition and subtraction, you look for the least precise, and you're always rounding it off based on that number. Like this example right here. This is to the 100th of place. This is to the first place. This is to the 1000th. This is to the 10th. I can tell you right now that when you do this problem, you better round off to the first place. And so the question here is, what is the correct answer? I don't even have to solve this problem though. The correct answer is 1520 dot. You need to put a dot there because this last digit needs to be significant. When you don't put a dot there, it tells you that's not significant. The 2 is the significant. Okay, this tells you 1520 dot, 1520 decimal is plus or minus 1. This tells you 1520 is plus or minus 10. So when you add all these digits up and you subtract 23, of course, is in there, then you will get 1520.000, 1520.00, 1520 dot, or 1520. The correct answer is 1520 dot. Okay, and again, it's because of the fact that your largest uncertainty is your 23 value, so you got to round off your answer. So it represents that the first place is your uncertainty. Okay, I hope that that's clear. That's a good example in terms of illustrating that. Multiplication and division is actually the simplest of the rule. And the reason why is because you don't have to worry about precision. You don't have to figure out how many decimal points to the right or to the left. All you do is figure out which one has the fewest significant figures, and you round off your answer based on that, 2 significant figures. Okay, this right here, I can tell you right now, without doing the math, I've got 2 significant figures right here. My answer is got to have 2 significant figures. Okay, which of these have 2 significant figures? It's 1.8. Okay, it's either D or E, no right answer. And if you do this math, oops, I don't know why I don't give you that answer, but if you do the math, the correct answer is the 1.8, because when you do this multiplication, you're going to round off to 2 significant figures. When you take 2 significant figures and divide by these, you're still going to have 2 significant figures. In multiplication and division, you're always rounding it off to the fewest significant figures in your data. Okay, so here are a bunch of examples that sort of illustrates that. Okay, this right here, let's see. This is when you take 35.2 and you subtract 29.0, what happens is, if you do this in your calculator, your answer will be to the 10th of a place. 35.2, put this in your calculator, 29, what you get is 6.2. Notice that these have 3 significant figures, but your answer is going to be rounded off to the 10th of a place, 6.2, but now it's reduced to 2 significant figures. Okay, it's reduced to 2 significant figures, and you can gain or lose significant figures when you add and subtract. 4 significant figures divided by 2 significant figures, well, your answer is going to be 2 significant figures. You have to round off that answer in your calculator to 7.8, because this portion right here reduces that bottom to 2 significant figures. Okay, here's another example over here. I can tell you right now that when you do this, you're multiplying by 2 significant figures here. Your answer better be 2 significant figures. I can tell you here that when you multiply this out, you're going to have 3 significant figures here and 2 significant figures here. And then when you add them, 2 significant figures here would be 0.089. 3 significant figures here would be 4.46. 4.46 is to the 100th of a place. 0.089 is to the 1,000th of a place. So you're going to end up changing that value to 4. Notice this is an addition, right? So your answer is going to be 4.4. Sorry, that's 4.46 and 0.089 is 4.549. You're going to round it off to the 100th of a place. So this would be, your correct answer would be 4.55. That would be your final answer, 4.55. And the reason why the 4 changes to a 5 is because the next digit over is a 9. So these, again, illustrates the power of significant figures and doing the math for that. So the only time you don't pay attention to significant figures is when you're multiplying a number by a definition. A definition is like 1 meter equals 100 centimeter. If I ask you, okay, I've got 5.876 centimeters. I mean, 5.86 meters. How many centimeters is that? You might go and look at this conversion factor and say, oh, my conversion factor only has 1 significant figure. No, don't do that. And the reason why you can't do that is because these are definitions. They have infinite number of significant figures. You don't round off your final answer based on these because they have infinite number. You base it on the data that you have, okay? And then exponents don't even count as significant. So the rest of these just kind of gives you more explanation on that. So hopefully that makes sense. Like this particular example, for example, okay? If a runner runs 139.9 minutes in 11 hours, how far will the runner have traveled in miles? Okay, so the original answer question has 4 significant figures. These are conversion factors, okay? These conversion factors are definitions. This has infinite number of significant figures. This has infinite number of significant figures. When you do the math, this is the number that you would get in your calculator. But go back to your original data. Your answer should contain 4 significant figures, okay? Because that, actually, this is a definition. Sorry about that. This 11 miles per hour, because that's a measured value, 11, and it's only got 2 significant figures, then you round off your answer based on that right there. So you would actually take this math calculation, look at your answer, and then round it off to 2 significant figures, because this 11 miles per hour is a measured conversion factor. Unlike 100 pennies equals $1, that's a defined conversion factor. You got to know the difference between a measured conversion factor and a defined conversion factor. 60 minutes to an hour, that's a defined conversion factor. 11 miles per hour, that's a measured conversion factor. You get paid $10.80 an hour, that's a measured conversion factor. Okay, so you got to be wary about that. So other things I want to talk to you guys about. Metric system, just know that in this class, we are generally always measuring things in the metric system. Like, for example, in experiment number 2, if you guys measure the length of, you guys are going to measure a bunch of things, like the length of a book. If you measure it in inches or your height. If you measure it in feet and inches, you're wrong. You got to measure everything based on scientific measurements, and the metric system is what we do. Take a look at that tutorial that I give you in, if you're in lab, on dimensional analysis. I'll also put it in the lecture, because this is a really powerful technique to solve a lot of problems. In terms of measurement, let me just do that real quickly, and then if there's no other question, No, there is no class tomorrow, okay? Remember that this class is an online class, and so we don't have set measurements, set meetings. It's basically, you guys are sort of learning things based on maybe review sessions that I have or lectures that I will post, but there is no set meetings. I apologize for that. But if you want, you can certainly ask me questions and I'll answer them. And then what I will do on a weekly basis is I'll put out a survey to figure out what's the best time for most people to meet. And that's why we have this. Otherwise, there are no class meetings. This is an online class, and there are no class meetings other than the ones that we set up on a weekly basis. Okay, and it changes depending on your schedule and depending on my schedule. So there is no class tomorrow. What about lab meetings? Lab meetings tonight at 8. Okay, that's why I put out that doodle survey out there so I can figure out the best time that in which most of you can attend. Okay, because we don't have any set time. What I want to do is I want to maximize the attendance, and so I send out that doodle survey to figure out when most students can attend. It seems like it's the evening on Thursday. Let me just finish this up with this following measurements. And we've already talked about measurements. And the reason why you need to know about measurements again is because of the fact that it's so critical in your lab as well as in chapter 2. So I'm going to finish up today's discussion with this, and then if there's any questions, then I can certainly answer them. But let me review this real quick because I do want to make sure that you guys understand the importance of what we are talking about here. Okay. This is part of experiment number 2, but it's also part of chapter 2 in your textbook. It's about measurements. And the key to measurements is to look at these graduation in a measuring device, because that will tell you the precision. Okay. So like I said, I already did this. See these differences here? You got to know the size of that first. And if you know that this is 20 and 30, then there's 10 marks in between, then you know that each line represents 1 degree. So that means the delta on this is 1, which means that your reading is to the 10th of that, 1 more digits over. Okay. So when you have a scale, the scale has no lines. All digits are significant when you have a scale. What you need to do is you need to press on this mass and see how this digit changes. If it goes from 6.50 to 6.51, then you know delta is 1. If it goes from 6.50 to 6.55, then you know that the delta is 0.05. So you have to actually figure out what the changes are on your scale to figure out what the uncertainty is. The uncertainty is based on which digit are you estimating. This right here would be plus or minus 0.1, because this next reading, if you press on it lightly, would be 126.5. Here, if you press on this lightly, it'll go from 6.50 to 6.55. So the deltas or the uncertainty is 0.05. You guys need to mute yourself. Okay.
Professor, you're on mute.
Sorry. Thanks. So when when your delta here is 1, right here is your delta, you're reading it 1 digit past the decimal. But you notice in this delta, it's 0.2. Well, when your delta is 0.2, then you're reading it one more past the decimal, but now in increments of 0.05. Okay. Here are pennies, 25.143 plus or minus all the way to the thousandth of a place, plus or minus 0.001. So here are rulers. You guys are all going to be using a metric ruler. Okay. From this point on, in all the measurements that you take in this class, your error is always plus or minus 0.01. All metric rulers measures two places past the centimeter scale. If you see that this is 3, this is right here, 1 centimeter, 2 centimeter, 3 centimeter. This is 3.1, 3.2. So your delta is 0.1. You're going to be reading it to one more digit past that, plus or minus 0.01. You can just see right here. This is 4, this is 5. That means this is 4.1, 4.2. Okay, delta is 0.1. You're going to read it one more digit past that. So that's going to be true for all of these. These are your graduated cylinders. This has an error of plus or minus 1 because the delta on these are 1 centimeters. This right here, the delta on this is 0.4, and the delta on this is I believe the delta on this is 0.2. Okay, so these are just examples of the errors that you have in your measuring device. Take a look at this. So let me just see. That basically is chapter 2. Okay, what I would really prefer you guys to do is when you're reading these things, come up with questions, because I'm not going to hit all the topics that you might find confusing. I'll hit the topics that I think are important based on my past experience. But if you are confused on some of the topics, you need to ask me questions. Okay, like you need ask for clarifying questions so I can make that clear in terms of my explanation. But I don't really like to rush things. I'm sort of rushing through these things because I spend more time on significant figures, which is important. But I think I could spend more valuable time on things that you find important rather than what I find important. Okay. But that basically is it. I will probably send out another doodle survey to figure out what time you guys want to meet next week. Okay. And I could answer any questions that you have on chapter 1, 2, and 3. Chapter 3 talks about matter and energy. The most important thing about chapter 3 is you guys need to know how to calculate caloric values of food. If I give you a piece of candy and I tell you you've got 2 grams of proteins, 3 grams of carbohydrate, and 0.5 grams of fat, how many calories does that candy have? If you are running and you expend about 500 calories per hour, how long do you have to run in order to exhaust all the calories of that piece of food? So that's next week. Okay, that's next week. Are there any last questions that you guys might have? I'm looking at the chat. Or
Yes. What do we need for our lab meeting?
nothing.
What materials do we need?
You don't need anything. I'll show you. I will point my camera on the scale. You might need to look at your scale because I'll show you how to use that. Then basically our lab meeting is just to make sure that everybody's on the same page, and then I'll show you a little bit about experiment number 1.